Welcome back, guys. Historically, inclines are very important to the development of physics. The earliest studies of gravity by Galileo used inclines to slow down gravity so he could study it. In his time, there weren't stopwatches, and things fell too fast, even if there were, to actually time it for gravity. He reasoned that if you had an incline and if you rolled things down it, as you made it steeper and steeper, it would be closer and closer to what it would be if you dropped it. And because of this, and a couple other reasons, inclines are a big part of physics. So I'm going to show you guys today how to do free body diagrams on inclined planes and also how to solve problems. So as far as we're concerned, we're only dealing with equilibrium to start with. So either this box is stationary or it is sliding down the incline with constant velocity. When we talk about the angle of the incline, we always talk about this angle. So this is the angle with the horizontal. This is common for everyday occurrences as well. If you've ever been in a car where it's very steep roads, they'll say there's a 5-degree grade, a 4-degree grade. They're telling you how steep the road you're driving is compared to 0 being a flat road. And 5 degrees is pretty steep. You'll see once we do the lab that something at 5 degrees will accelerate at a big rate. Given your FBD, the angle of the incline is going to be the upper angle of mg. So in our picture here, going back a slide, this is in equilibrium. So that means that this arrow plus that arrow plus that arrow equals 0. Now, how could that be so? Well, it turns out that this arrow is doing two things. Part of it is opposite the normal force, and part of it is opposite the friction force. To make this more apparent, we're going to rotate our entire FBD. Once you rotate the FBD, it ceases to be an FBD. A free body diagram tells us all the forces on an object, and it also tells us their direction. By rotating it, I'm changing that direction. So I'm going to take it from the top picture. I'm going to pick up my free body diagram off of the smartboard. I'm going to spin it and put it back down so that my normal force is straight up and my friction force is straight to the side. And now the only thing at an angle is going to be the weight. And I'm saying this angle here is the same as the angle of the weight. And so that means that this component, in this case, would be F1 cosine of alpha. And this component would be F1 sine of alpha. And I'll try to convince you of this as I go through. All right, so looking at this picture, I'm going to scroll so we can see the whole thing. This is the angle we're talking about. Again, we're always talking about what that angle is. In physics, our generic angle is lowercase theta. All right, I'm going to do a free body diagram on this. I know that my normal force is normal to the surface, so that should be perpendicular. And I know that my weight goes straight down. So I'm going to extend this line down. If this is the level ground with this line extended down and this is theta, the angle between the dotted line and the ground would be 90 degrees. So now I know this side is 90, this side is theta. I don't know what this side is in here yet. Well, how could I find that? Well, I know that all of the angles in a triangle add up to 180 degrees. And so that means that whatever this angle is, blank, is equal to theta plus, whatever this angle is, plus theta plus 90 is equal to 180. So whatever our unknown angle is, plus theta plus 90 is equal to 180. So this unknown is going to be 90 minus theta. Is equal to our blank. So I'm going to put 90 minus theta in here. And it should make sense, right? Because I'm doing 90 minus theta plus theta would be 90. 90 plus 90 is 180. That's a triangle. Okay, so I'm going to look at the normal now. The normal is perpendicular. So if I extend a line that is parallel with the normal going this way, I'll change my colors. So it's going to be parallel with the normal going this way. You would say the dotted line and the incline, the angle here would be equal to $90, because it'd be normal. Then this angle we don't know, but this is the upper angle of the weight, and this angle together should all add up to 180 because it's a straight line, right? A straight line is 180 degrees. So I should have 90 plus our unknown angle plus 90 minus theta equals 180 because it's 180 degrees in a line. So what needs to go in here to make this true? Our blank must be theta. So that tells me that this angle there is theta. And so that's why this angle and that angle are the same.